Hello and welcome to Digital Futures tutorial series. Today we have a very interesting tutorial and it is in continuation with our first tutorial on generative game. This session will look at 3D GAN and it will extend to the learnings which were done in part 1 tutorial. We'll talk a little bit more about this tutorial, but before we begin, I would also like to remind our audience about our first Portuguese language session, which is going to have super exciting speakers from ICD, from Zahadi Architects. This session is going to take place at 2 p.m. EST. We have shifted with the clock, so be aware of the timings that we are looking at here. The next in the series for this weekend is another session by Digital Futures and FIU. This set of series brings together leading thinkers from AI, neuroscience, and architecture. The event will be hosted by Professor Neil Litch and with our distinguished guest, Suzanne Schneider, who would be talking about her topic called Artificial You. And amongst the other upcoming session next week, we have another of our Digital Futures Farsi talk, which is going to talk about multidisciplinary approaches in architecture. This session will take place on 25th of March, Friday at 11:30 a.m. EST. And followed by that, next Saturday at the same time, we are going to have another talk session in English, which will host some interesting ideas on clay printing in architecture. I would also like to remind our audience that we have all the materials available for our tutorials, for our talks, for doctoral consortium on our YouTube archive. You can check out the link which is posted on this on your screens. And we are now looking at recruiting some of the new team members, and please reach out to us if you're interested in joining, giving volunteering for any of the positions during our summer festival. Join our community on Discord. We look forward to receiving your applications at info@digitalfutures.world. Without further ado, I am going to give the platform to our very interesting guest, Jen, who would be introducing himself and be talking about the tutorial furthermore. Jen, the screen is all yours. Please introduce yourself.
Yeah, thanks for having me and all the DF team for organizing this amazing event. Yeah, today the original lecture will not be able to make it, so I will be taking over the tutorial session, and basically we'll be doing the second part of the generative game with a focus on the 3D generative adversarial network. And yeah, I'm Jen. I'm a creative technologist, a machine learning researcher, and also a Web3 enthusiast. So let's start this together. So in our previous session, yeah, we went through some of the basic implementations of the 3D GANs using the Colab notebook provided by Ruja. And as you can see in last part of the previous tutorial, there is somewhere you can export your files as the PLY and as a PLY, and you can then export that into your local environment after you create the inference from the 3D GAN model. So yeah, but all those are just the raw point clouds and voxel data that are, we need some ways to further visualize these cool results from our 3D GAN. So that's what today's session is mainly about. So yeah, the last part we mainly focus on the basic concepts of voxels, how you can acquire and preprocess the 3D data for the 3D GAN training, and how you do the 3D GAN training actually. So, but this part will be focused on the post-processing and visualization. And today we're going to go over like mainly three parts. So the first part being the graphics pipeline. So mainly introduce how the computer graphics industry do the rendering pipeline from the 3D mesh into a real like rendering. And the second part will be covering the basic knowledge of shaders, which is like the most important and powerful tool for visualizing your 3D objects and see that on the screen or like a electronic display. And the last part would be focusing on some advanced visualization techniques, particularly using like Unity for Unity visual effects graph and particle effects for making your 3D GAN objects a cool visualization. So that's pretty much the schedule for today. Yeah, so before we like dive into the technical details of the visualization, yeah, like one important aspect that motivates this tutorial is the commonality of the visual effects, which is usually abbreviated into VFX in the CG industry. So yeah, for most of the movies or animations or games, you see that has a really high quality, high fidelity rendering. It's actually like like the geometry itself might not be as sophisticated as the as what you see on the screen. Like this is actually a comparison for one of the animations. It's like a house flying around the world. Sorry, I forgot the specific title. Yeah, but yeah, as you can see from the picture, the comparison for the 3D model you create, for example, in Rhino, and the one that's actually get rendered is quite different, right? Like on the left side of the screen is what you do in the modeling engine. So basically like a very low poly mesh system, and what you scan on the right is like a really high fidelity. You can see the balloon is very smooth, and you have a volume of hair on the people. But in the real rendering, you have a very delicate fur system that gets rendered on the screen. So how is this process achieved? This has a lot to do what we call the rendering pipeline or the CG pipeline. So basically, the CG pipeline is like the entire process of how you can render a 3D objects from your computer memory into a computer screen. And this process involves a lot of like mathematics, but thanks to like all this advancement, we do not need to deal with all these technicalities of ourselves. So a lot of them, like the Grasshopper, already have some of the basic rendering functionalities, and Unity has even more functionalities for this rendering process, like shader graph. You no longer need to write some of the code yourself, even by using a visual scripting interface. Yeah, but yeah, we still need to look at what's really happening underneath to really understand like the how the CG pipeline works. So imagine that you model something in Rhino, and you have a camera that that you can navigate in the Rhino virtual space. So yeah, you have some 3D mesh out there, and each of the mesh is actually composed of some really tiny triangles. Even in Rhino, after when you create the NURBS, it's actually rendered as a mesh. So no matter how complex your geometry looks like, it's usually converted into the mesh for the rendering. That's what basically most of the determined by the GPU infrastructure in terms of the hardware. So because our GPU are so optimized for rendering the triangles, yeah, we like the software set is also like implemented in such way. So imagine you have like complicated NURBS that you modeled in Rhino, and yeah, it's subdivided into multiple triangles. And there are a couple of approaches that are involved into rendering this into a screen. So the first approach, you're gonna calculate how this point is gonna be projected onto your screen. So this is using like a homographic projection matrix to transform the object's coordinates into 3D from the 3D into a 2D screen. So it's basically you can imagine this as a just something that like taking a picture using your camera, right? So everything in the real world have some coordinates related to the world origin, whichever you define, and your camera has also have a coordinate. So by using the coordinates of your camera, the world coordinate, and the coordinate of your object, you can calculate a projection matrix from your object into the camera screen. Yeah. So yeah, we don't need to worry about the real math behind it, but that's how things actually works. Like it's actually projecting this XYZ value of your mesh coordinates onto some XY value on your screen. Yeah. And once you get all these coordinates, there are two things that are really important in the rendering process. So both of them are called shaders. So what shaders is actually what is giving your objects color and look on the screen. So, and the shaders have two parts. The first part is the vertex shader. The second part is the fragment shader. So vertex shader takes charges of like doing some manipulation in 3D space, like how you project your coordinate from the workspace to screen space is actually done by the vertex shader. And we can do some cool manipulations in the vertex shader by, for example, like you can let them move up and down across time, so it looks like an ocean. And what's more important is that once you get the vertex shader, use the vertex shader to project your 3D space, 3D object into the 2D screen, you have to give it a texture or a color to render it, right? So after vertex shader, you can imagine that you have a black and white world or like a wireframe world that has nothing get texturized. So what fragment shader does is that using the fragment shader, you can tell the computer on which pixel of your screen I want which color to display. So for example, if like there's a red cylinder here, so I want the pixel inside the red cylinder area on the 2D screen to be red. So that's what fragment shader does. Yeah, do not think that as too much of a complicated stuff, but it's just something that that projects project your stuff from 3D to 2D, and then give your 2D wireframe a texture. And then you can get a render mode in Rhino. Yeah. So there's a really nice visual explanation taken from YouTube. So I think I posted a link here, but yeah, I'll send it in the chat later in case you want more reference. Yeah. So as you can see here, it's still same animation. Like we want to determine which point on the screen should be rendered. So this one is actually a part of the blue balloon in the 3D space. Yeah. And you use like some back projection from the camera, basically ray tracing or like to the 3D space to intersect with your mesh to determine like which triangle is going to be rendered here. Yeah. And as you can see here, in the previous part, like the screen is actually composed of very tiny pixels, right? In Photoshop, or in like just computer image, if you zoom in, each point is actually a small pixel. So yeah, this pixel is what we use to give each of the point a texture. And we sometimes also add lightnings and bump map into the texture, into the pixel to visualize some of the lighting effects or the material effects. Yeah. So that's the conceptual elements of establishing a CG pipeline. And then we're gonna go more details into how this is implemented. So like there's a very important data structure that almost most of the computer graphics platforms provides the API for, is the vertex attribute. So in each vertex of your mesh, you can store some attributes into each vertex. For example, the XYZ value, which is the 3D coordinates of your mesh vertex. And you can also store other vertex attributes, such as the RGB value of that mesh vertex, if we want to render the mesh purely with color. Or you can pass in some UV for the vertex that you want to sample from a 2D texture image. Like, for example, we have a texture for like a mesh, and each of the points each of the vertex in the mesh like have a UV value that you can sample back into the texture, 2D texture, to actually like display the texture onto the mesh surface. Yeah. So this is a very flexible data structure. You can basically store anything into it. Like Rhino provides some of the APIs for accessing most of the vertex attributes. And you can, in the latest Rhino 7 version, you can also add new customized vertex attributes to your mesh vertex. And you can also access them from the shading programs. So yeah, basically that's the first important concept, vertex attribute, which stores all the information you have to use for rendering your mesh. And we're gonna also see, like in the following tutorial, how these vertex attributes can be used to create some interesting visualizations. Yeah, this is not a good example, but it shows how you can use vertex shader to control the displacement of your mesh. Like, for example, in this case, it's a 3D model of someone. It's actually a model from Unity, like the default templates. You can use this vertex shader to offset the vertex of the like a 3D mesh to create some interesting effects. Another common usage of the vertex shader is to create water or like wave simulations. Like your mesh vertex is actually like moving up and down, following some sine function or cosine function through time. So you can set the vertex attributes to something that plus or minus like a sine of time in the vertex shader, so that it looks like a wave surface instead of a static surface. And with fragment shader, there's even more cool stuff that you can do. So there's a lot of fun playing around with fragment shader, because you can actually control how your mesh looks through the texture. And this is all the VFX visual effect is about, like how you display like your texture in a cool or special way. It's mostly done by fragment shader. Yeah, one of the practical examples of using fragment shader is that like the normal maps that you use to render some complicated material, such as like a rotten wood or like brick walls, where there's the tiny there's the tiny like bumps on your surface that are too expensive to model with geometry. Like if you say the alternative way of doing this is that you can actually model this bump in Rhino, like by manipulating and the control points of your NURBS, and you subdivide it into very tiny pieces. But this is very expensive, right? To save the to save the computing source, but while also getting the same effects, we can use this normal map techniques to just we tell each of the vertex, each of the fragments, oh, you have to offset to this particular height, so that it looks like there's a bump inside the surface. Yeah, it's much cheaper and very efficient in terms of visualization. Yeah, and there's a lot of fun playing with fragment shader as well. Like you can like display different colors on the 2D surface depending on the place of the vertex. This is one of the example from Shader Toys. I strongly recommend you to go over this website, because there are just so many cool effects regarding fragment shader in Shader Toy. And Shader Toy doesn't really have the concept vertex shader. It's basically a playground for fragment shader. So there's if you're really looking into learning more about fragment shader, shader tool is definitely like a really nice resource. Yeah, all of these cool effects you can code them yourself using the fragment shader. And yeah, there's also some very advanced fragment shaders where you can even create geometries. Like for example, this one I believe that is using remarching algorithms to create all these geometries. So you can see it's kind of like a metaball effects where these volumes are interpolated together in a very smooth way. And all this small program is creating fragment shader only. Yeah. Okay, so yeah, after we go through all of those concepts, how can we like leverage the power of shaders and play with it and get our hands dirty? Luckily, Rhino 7 provides a new functionality called GHGL. So it's basically the Grasshopper shading language. And you can install that via Rhino package manager. Yeah, and today we'll be mainly introducing some of the basic functionalities of the GHGL and how you can use this to like visualize your output from the 3D GAN. Yeah, this is one of the sample effects. Like you can do some cool color gradients on your NURBS or your mesh in Rhino. Yep, and I think Behavli has already set this into the chat. Yeah, for like, yeah, you have to install this to like dependencies in order to make everything work. So the first one is a mesh processing library called Chromodoris. So the second one is the GHGL itself. The GHGL can only be installed via package manager, I think, in Grasshopper. Sorry, in Rhino. Yeah. Okay, so that's that's like how you can set up the environment for shaders in Rhino Grasshopper. But before we dive into the details of the shaders, yeah. Okay. Yeah. So far, have anyone have any questions regarding the existing content? We'll be mainly doing tutorials from this time on.
Yeah.
Okay, cool.
Yeah, we can go ahead with the tutorial bit. Yeah.
Awesome. Yeah, so before we start to dive into the details of the shaders, yeah, we'll first, do some format like management of our PLY data from our previous session. So a little bit background information about the PLY file formats. Like the PLY is the point cloud data structure that you can store like points inside it, and there are basically 3 different formats for the point cloud. Sorry, for the PLY file. The first one is called format ASCII. So basically, that's a text-based format for like PLY, and there are also binary-based PLY big and little endian. So yeah, then unfortunately, like Rhino and Unity read each of those differently. So we have to create a formatter for our PLY file that we generated from the last session. Our last session actually using the ASCII format because it's more compatible to Rhino. And now for this session, I created a converter for the binary little endian converter from Rhino, for Unity that I'll be using later in the session. If you do that incorrectly, like importing binary to Rhino or ASCII to Unity, they will complain, yeah, like this. Okay, so let's first do some live coding regarding the shaders. And right before this, I'm gonna really quickly show how you can convert the point cloud that we have from last session into the correct format for Unity first. So yeah, this is the same notebook that we used for last time. Yeah, if you run everything correctly, Yeah, if you run everything correctly, you don't need to run all the training sessions. You can directly jump into the inference part. Yeah. Here you have to replace the path argument, whichever path you store your generator checkpoints. Remember, we have the g.pth file is what is the generator checkpoints for our 3D GAN. Yeah, and we also have this kind of like a obj path, which stores which direction you want for your like output like PLA file. Yep. So once we not this one. So once we have that, we can start generating some like latent work of your 3D geometry. Yeah. So basically, if everyone recalls from last session, the number of vector arguments represents how many points you want to sample from your latent space of your 3D GAN. So basically, that's how many different shapes you want from your 3D GAN latent space. And the number of learn step is how many in-between values you want between the to visualize a smooth transition from shape A to shape B inside your latent walk. So yeah, so for example, in this one, I sample 10 different chairs from my 3D GAN chair latent space. And between each of the different chairs, we have 10 steps to interpolate between the different two shapes. Yep. We're gonna be using this to quickly export like a sample OBJ like ASCII format document. So if everything runs correctly, you should see all of these logs here. Yeah, it's basically writing OBJs into your like Google Drive. Yeah. Once you finish this one, I will just not go through all the details of running it. You can run this one, which is kind of updated version of the from the previous session. Yep. So so for this one, yeah, it's basically we use this what is called a PLY file. It's a Python library for processing the PLY file and translate the between different formats of the PLY so that we can use in different applications. So you can just run this cell and replace the OBJ path and output path. OBJ path represents your ASCII PLY file formats, like repository, and output path represents your binary PLY file, like directory. Yeah. If you run this correctly, you should also print out all those file names for your like ASCII like PLY formats, PLY files. Yeah. Yeah. So once we have this, then we can go ahead and jump into the jump into the wrangle part. Yeah. Okay.
Yeah. Can you also share the links to the Colab files?
Sorry, what is it? The files?
Yeah, the file that you were working on. Can you send that? Some of the students are asking. The Colab, Google Colab link that you had just opened.
Oh, the link. Okay, sure. Yeah, I'll post that again. I think we already have that before. Yeah, so this is the Colab link that that we're currently using.
Yeah, thank you.
Yeah. Okay. So that's pretty much it. Once you have the OBJ file, just store that into somewhere onto your computer, and we'll use that later. Yeah. Okay, so yeah, after you explore the OBJ, the PLY files, yeah, we are done with all this like Colab part. Like you don't need to mess with the Colab anymore. And then we can import the PLY files like from the Colab export into random Grasshopper. Yeah. But before we begin to handle the point cloud part, yeah, we can take a simple look at yeah, how the Grasshopper shader language works. Yeah. Can everyone see the screen share of the Rhino now? Okay.
Yes,
yeah.
we can see Rhino.
So yeah, just a quick demo for how you can install GHGL. You just click type into package manager inside your Rhino command line, and then you type GHGL into the package manager, and then it should be there. Yeah. Yeah, just install the latest version. You have to restart Rhino if you're the first time installing the GHGL package manager. And yeah, also Rhino provides some of the like quick starter files for the GHGL. Yeah, I also post it here in case you want to learn more about that in the future. So yeah, but we'll be go over some of the files together to see how that works. So basically, what GHGL is, if you after you install the program, you can just type in shader inside your Grasshopper command, and then you can see there's a couple of new elements popping up, including the shader. This is the basically like shader object that Grasshopper wraps around, and also this is this is like a GH shader, which kind of like renders the points for your Grasshopper program. Yeah. And what we mainly using more is the GL mesh shader. Is actually what you use to render your mesh. Yeah, but using this GL shader version, you can also use that to render some of the points in the Grasshopper. For example, this one is basically subdividing a spiral curve, and it takes multiple imports, and you can configure the import ports as much as you like. Yeah. So for this one, it's basically very simple. If you double click on the GH shader file, it will pop up a window, and you can see all these sub-shader programs inside the shader, the small shader. So basically, this is what we just talked about. The Vertex shader is basically just projecting your vertex, from the world space to the screen space. Yeah. So there's complicated math behind it, but basically what it does is just multiply a word to clip MVP matrix to your vertex 3. Vertex 3 is transformed into vertex 4 because there's it's a kind of homographic space. Sorry. To do you have to be a homographic space to do a homographic transformation. So it's basically appending one after the vertex 3 of the vertex, and then multiply by the 4x4 word to clip matrix. Then everything is transformed from the 3D space into the 2D or the screen space. And once you have that, you can use the vertex color to render whichever points here is inside the screen. Yeah. So yeah, I believe we are passing in a sequence of I think it's basically a sequence of it's using the t value to sample the color from this gradients components. So that you have if for example, if you have 700 points, then we're gonna also sample 700 vertex colors from these gradients. And each vertex color is parsed in as what is called uniform. Yeah. So as you can see here, Grasshopper uses this in syntax to take in the uniform variables. Sorry. So to take in the uniform variables. So for this one, this GHGL shader is slightly different from the mesh shader, but what it does is that basically the same, is just rendering the points. Oops, sorry. Then we're gonna move over to see some of the other examples of more complicated versions of the GL shader. Like for example, this one is this is still a GL shader. Yeah, this one is a mesh shader. So as you can see here, we can use the swatch to give the mesh like whichever color you want to pass into the mesh. Let's say, for example, yeah, if you want to pass in some different colors, you can separate from the swatch. Yeah, this is more of a standard GL mesh, like mesh shader program. So you have what is called like a mesh vertex attribute called passing from the layout statement in the shader program. And you also have these uniform values which you pass in to render your mesh. For example, the material color. Yeah. And all of these, this like syntax language is called GLSL. So it's what is OpenGL shading language. Yeah. So it's very similar to C if you have programmed C before. Yeah. Sorry, this should be there's yeah, this should be the double slash for comments. So this is the GLSL language that most of the shading programs use, and it always follow a certain pattern. So don't be scared by this one. It's usually actually very simple sometimes. So it usually starts with the title version. This one tells you which version of OpenGL you want to use. So you do not need to change this in Rhino. Basically, like mostly is defined by Rhino already. So it's like the minimal version. I think it's a minimal OpenGL version that can function correctly in Rhino. And then here comes what we call here comes first. Let's look at the vertex here. What we call vertex attributes. So vertex attributes is mostly what you pass into the vertex shader programs. So let's say, for example, this mesh vertex is actually the XYZ value of your mesh vertex. And the mesh normal is the normal vector of your mesh. Yeah. So if I bake this, sorry, not this one. If I bake this geometry, you can see this one is rendered as a NURBS, right? Here in the Rhino as a NURBS. But what actually really renders it is actually mesh. So let's say we can just simply transform that into a mesh by calling this mesh function. Yeah, let me hide this NURBS geometry. Yep. Then you can see the NURBS is actually rendered in the formats of a mesh. Like each of the points is actually part of the the vertex. Each of the points is actually like the mesh vertex inside this one. In this case, it's actually each of these particular points in your Rhino geometry. And this mesh vertex is basically the vertex XYZ value for this particular point. Yeah. And mesh normal is what is getting computed for as a normal vector of the surface at this particular point. So each of your mesh face have a normal. Is basically what is perpendicular to your mesh face. The vector that is perpendicular to your mesh face. Yeah. With these two values, we can do a lot of fun stuff. For example, we can even like send the normal further to fragment shader and play with the normal. And for the like vertex, like mesh vertex position attribute, we can use that, as we mentioned before, to project this vector 3 into the 2D screen. Yeah. And using the GL position, we can calculate the UV sometimes if you are sampling the color from a 2D texture. Yeah. But in this case, it's pretty straightforward. It's basically it's doing some of the intensity calculation depending on the light and the camera position. But eventually, what it does is passing this, creating this vec4 for the fragment color. So fragment color is what finally tells you which color I should put for each of the face on my screen. Yeah. We can also, I think we can also omit all of these parts. If we can do some experiments here by omitting all these parts, and you can directly pass in the material RGB into your program to comment it this way. Yeah, we can to the fragment, to the arguments of the fragment color. Let's say we pass in the it actually itself is a vec4, so you do not need to worry about that. Yes, I think the material color is here we have this vec4. Here we have this vec4, and we comment on all of these. We have the material color directly as our output vector. Yeah, so as you can see now, whichever color we put here will be rendered on the screen. Yeah, so that's the simplest fragment shader you can create. It's basically giving your mesh a certain color. Yeah, based on your input. And the color here in Rhino is represented as a 4 vector. So the 4 vector, vec4 means the 1/4 vector. And here the vec4 is represents an RGBA channel of your color. So let's say, for example, this one is the color is 0, 120, 225, and 225. And the vec4 is basically the same as your like a vec4 color composed of your RGBA value. Yeah. So that's the very fundamental concepts of your of the first Rhino GHGL shader program that you can write. And also a quick note is that everything happens like inside the shader is inside the main function. It's the same in the vertex and the fragment shader. Whichever code you put, it's gonna finally be rendered inside the main function. Yeah. The uniform is what we pass in here on this interface as some of the external variables. And there are also some built-in uniforms that you can get from Rhino, for example, the light direction and the world to camera normal is what we basically use to calculate the bob maps. Yeah, and you can find all of these built-in uniforms from here. Yeah. Also, frame size means I think it's the width and height of your current screen. And the built-in attributes is what you pass in as the vertex attributes from your Rhino program. Rhino only gives us this kind of 4 attributes, and the mesh vertex is actually the position of your mesh, which will be used most. And then mesh normal is the normal vector of your mesh face. Texture coordinates is what we call UV that you use to sample, like from a 2D image. And the mesh vertex color is the built-in vertex color for your mesh from Rhino. If you, for example, if you draw your mesh with some color in Rhino, then you can access the vertex color here from here. Yeah. That's pretty much the basic structure of GLSL. Yeah, so we have this, recall that again. We have this vertex attribute input, and we have this uniform input. Some of them are built-in uniforms, or some of them are what we pass in. Yeah, and apart from that, we use this alt syntax to pass in value between the vertex shader and the fragment shader. So if here we have a vertex string called normal, then here we can have a in vertex string called normal. They do not need to be the same name, but they have to be the same type. Oh, sorry, I think they should have been the same name as well. Yeah. So yeah, and what this is usually called varying variable in the in the GLSL shading language. You can understand that you can pass in something from vertex attributes to fragment attributes. For example, the mesh node, that we usually use. And we can take a further look at the original example. It's nothing special, but taking the light direction and the camera position to make your rendering more fidelity, high fidelity. Yeah. Okay. So that's the meshed one example provided by Rhino. Based on that, we can probably have some more fun stuff to play around. For example, this one. I think we can also, instead of using the existing example, we can also customize our own meshes, I think. Yep, here's another point. Yeah, this example basically shows you, the example of gradients. So that shows you how powerful our shader is. That allows you to do a lot of interesting visualizations. For example, what if I want to render our mesh based on the vertex proximity to some 3D point in the in the Rhino workspace? This is how you do that, and you can see this is changing in real time. So first of all, if you recall from the previous one, we didn't have the we didn't have the the uniforms that you can customize on your, for example, on your shader program, like the 0.0, 0.1, color 0, color 1, especially what you use for basically what you use for the for the shader program. You can pass in all those points and colors from the uniforms. Like if you want the 2 points as the point you want to determine which vertex should be rendered. Yeah, this is where you're passing the 2 points as the uniform in the form of the vector string. And you can also pass in the color for each of the points that each vertex is closest to in the form of a vector color. And in this case, we can compute a value for each of the vertex, like their distance to the point string. This is computed using, it's basically projecting, creating a line between these 2 points and projecting this vertex onto the straight line. And depending on the parameter between the 2 lines, it will give a value between 0 and 1 to determine which color this vertex should be rendered. So basically pass a float called inline t to the fragment shader to determine the color that we want to render for each of the vertex. Here we use like a mix function to mix between 2 different colors in this GLSL program. So yeah, these are some of the simple examples that you can see from that Wrangle provides. So I've sent a link to the chat for this one. And does anyone have any questions regarding this?
I think there was a question. If we make the mesh a bit more high resolution, does it affect, and how do you kind of go about the code, or does it compute with the same within the same time?
You mean like a mesh? You mean like a high resolution mesh?
Yeah, yeah. So if you increase the resolution of this current mesh, is it a better result? How does it affect the result?
I think it's like the resolution of the mesh shouldn't be impacted so much the result. It's basically like what is processed on your GPU. So it's pretty efficient if you're asking about this in terms of the performance. Yeah.
Okay. Okay.
Yeah, you can actually subdivide your mesh, I think, using some. Yeah, I'm not sure whether I have installed Vivibird here, but yeah, I think I have the Vivibird subdivide. Haven't used this for a long time, but yeah, you can use the subdivide function in Vivibird to test. You know, like
Okay.
yeah, to test. If you further subdivide the mesh, it should be fine as well.
Yeah, yeah. Makes sense.
Okay.
Okay. Yeah.
Yeah. So now let's create a new document and we can start experimenting rendering our like 3D GAN objects using this GHGL like shading language. Yeah, so we're gonna start from a simple like Python script to customize our file import. Yeah, this should be very intuitive. Yeah, so basically what you have to do is you have to import OS and you have to import glob, and you have to import. Yeah, you have maybe have just need to import glob. Yeah. So what we do is that we first glob all the files, glob x plus. Yeah, so this is basically this glob syntax to help you retrieve all those files from a certain directory. Yeah, and then we retrieve all the paths inside that repository by using a simple for loop. We can change this variable name to pass. And we keep that type hint of string. Okay, now that we do not yet have a path here, there's nothing here, but yeah, this path is basically what where you store your like 3D objects. So let's say, for example, if I store my yeah, if I store that onto somewhere like C's, some users desktop or stuff like that. Yeah, then you just use the panel to add this repository to here, and then yeah, you can just run this one pretty fast. I'll be typing my file locally. Okay, so yeah, you can do that by pasting, just a copy and paste this directory from your from your file explorer. And once you have these, yeah, you should see that there's like a couple of, you should see there's a couple of files that are, I guess, generated. Yeah, let's say, I'm sorry. Yeah, let's say, yeah, here, like I have stored them under the Dropbox Generative Game, like, yeah, all of blah, 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 and now zip them onto the objects. And if you get everything correctly and you internalize all the data here, you can see all the files are printed out using this wrangle Python script. Okay. Then we'll be reading some of the files using the list items. We're gonna retrieve them from by using like a number. Like for example, retrieve the 20th elements of that, and then we're gonna create another C# file, C# script to read the ASCII file of that we downloaded from the Colab. So as you can see here, our PLI file is nothing special, but just a simple text. So this is one of the PLI file that I get from my 3D GAN generation. Yeah, the ASCII format PLI file, if you open that with the code editor such as VS Code or Visual Studio, you're gonna see all this kind of stuff, like which begins with the PLY and format ASCII. And you're gonna also have a count of how many vertex you have here for your PLI file. And then I can only have XYZ value, so it will show property float X, float Y, float Z. That's basically the header part of your PL file. And what you do with our C# script is that we basically parse all these XYZ values from the PLI file, and then we transform that into like 3D points. Yeah. The GHGL samples, I saw a question from the chat. Sorry. The GHGL sample is basically, yeah, I think I provided that into the chat. I can send that as well, again as well. It's basically provided by the Randall McNeil official repository. Yeah. Yeah, then let's go back to the Rhino part. Yeah. Yeah, so once you have the path, you can read that from the C# script, and you can parse that into like 3 points. So we're gonna just leave it called A. So yeah, basically what we do is that we're gonna move through like each line in the ASCII file and just separate the line with comments if they are numbers instead of the header file. Yeah. So to do this, yeah, and we're gonna also create a list of points 3D based on this file. So we first created like a list of points. Yeah, so basically just and we gonna use the system.io to read all the files. Use the system.io.stream reader. read from the file. It's a bit of this is not existing in the default API. This is how you create a stream reader using the wrangle, using the C# system file built-in class. Okay, it's running correctly. Yeah, and then we're gonna create a while loop for how we read this one. So yeah, each of the stream reader objects has a method called readLine. Like we're gonna loop while this line is not empty. We're gonna parse the content. It's separated by space, as you can see from the Visual Studio code. Oh, sorry. Yeah, we're gonna separate each of the line with the empty space. We're gonna read out. We're gonna parse out the XYZ value based on the index of each of the content on each. Yeah. And then we're gonna add a new 3D points to our point list. Okay. We can also close our file. We're gonna lastly, you're gonna export the files. Tracing narrow. Okay. Oh, sync is missing something. I have to add a yeah, this net is kind of like really strange sometimes here for the file reading. Just quickly double check. Oh, sorry, I forgot to. Yeah, I have to declare that. Sorry, first. Yeah, so the line object is basically what you read from each of the line from here. Yeah. Input string was not in the correct form. It means that we cannot split everything from this one. Oh yeah, I think that happens is because we have this header, what we call the header part of the file. It's on line 1 to line 7, basically. Yeah. Yeah, let's then skip those lines and try to use a counter. We can use a counter. Yeah, set a counter to 0. Increment that by 1 each time. Order is less than 8. We're gonna not doing anything. Okay, now it turns out to be good. Oh, great. We have this 3D points here in random. Okay. Yeah. And you can also see that we can translate that into a point object. Great. All right, let's see how that looks in the white background render mode. Nothing. Okay. Yeah, you can also do some fun stuff here by assigning the random color using the point visualization as well. Yeah, but we're not going to do that because we're going to mainly focus on how we interpolate it into a mesh. So here is where we're going to use the Chromodoris library. So yeah, now as you can see, it's basically a bunch of points, right? How are you going to turn that into a mesh? We're going to use this magical component inside the like a Chromodoris called build ISO surface. Yep. So sorry. Yeah, we're gonna build voxel samples, sorry, from this tiny points that we have already got. You have to improve the size, I think, and also the efficient range, which is the required argument. This one is just heuristically, I used 10 to 15 something. Basically, it generates a voxel box for your input points. Yeah. And what's actually doing the magic here is this one. It's sampling the ISO surface. Calculates the ISO surface from the voxel data XYZ and a box. You can understand that as sort of like remarching algorithms. Sorry, get it wrong. Marching cube algorithms that kind of like compute the mesh value for your given your like point inputs. Yep. Great. Now that we have a mesh here. See what we got? Yep, you have a mesh that is composed of all triangles. And then we're gonna, and if you change the index here, oops. I'll be careful about this one. It's kind of like expensive, I think. Yeah, then you can see that the mesh is smoothly, it's changing smoothly as you slice through different values. This is basically what we call a 3D latent mode in real time, right? You slide the sliders and you get different mesh shapes here. And now we're going to further do some visualization of our mesh objects. So one simple quick technique that we can use is to create a bounding box for this one and rotate the mesh around some certain angles. So I'm going to rotate that with respect to the bounding box. I'm going to rotate that to the with respect to the center. think it should be the box property instead. Here we go. I'm gonna rotate that around the center of the bounding box by giving it a rotate angle at 2 radians because this one takes in the radians. Okay. We're gonna from the rest of them. Then you can have a rotating chair here in the Grasshopper. Okay. Yeah, this is just a very simple visualization. And then we're gonna do some real stuff. We're gonna write a GL mesh shader program for a mesh. Yep, but now you can see that there's actually nothing on the screen because the default mesh shader doesn't really have anything. It's basically giving like a random diffuse color. In this case, 10011. Yeah. I think we can slightly play this. It's very dark, right? Like we can slightly play this one to yep, to further some visualization. Yeah, let's first forget about all these like options. Now we have purely white chair. Yeah. Well, the most basic stuff you can do here is passing some simple color for your mesh. Use a swatch. And you have to add these as a uniform. Then you do not need to hardcode the diffuse. You can just say, let's say diffuse then equals to color. Yep. Then we got something. Arrow. Have this red for color. Oh. Okay. Now we have the color mesh here. Just 1 second. What we can also do here is that we can also add some texture to our mesh instead of just the real color. To do this, we're gonna need another, we need to copy our Python script actually to read from our image folder. Let's say, we, for example, what I have here is I generated some like images from the neural network. Basically, it's just a random cloud. Yeah, I'm gonna use these images as my texture for the mesh. I'm gonna paste the images to the Rhino the Python script input. Okay. Yep, as you can see here, if you get everything correct, you should have all these objects. And we're gonna use another reset to sample from these images. Like we can use a simple index that has an image and perform some visualization. Yep, for example, this one should be different if you change to indexed. And we're gonna use this image object to as sort of like the input for our mesh. Yep. How are we gonna do that? Yes, as you can see, we previously talked about the mesh vertex attributes. So we can use another attribute called UV. It's in one of the built-in uniform, and it's called mesh vertex coordinates. Yeah. So yeah, we can either call it we can just call it UV, and we're gonna pass it from our vertex attribute to our vertex shader to our fragment shader. Let's call it UV. And now UV should be the same value as the mesh texture coordinates. And then you pass in the UV from the vertex shader to the fragment shader. Yeah, that's how you get the UV of your mesh. Then we're gonna also get try to get the image. The image uses a different uniform type. It's called sampler 2D. The sampler 2D means that it's an image. Okay, I'm gonna add another column called texture. Otherwise, it's gonna be yellow. Okay. Now you pass in the texture to here. See, this one shouldn't be named texture, I think. Or sorry. Or I named it incorrectly. It should be smaller as that's sampler 2D. Okay. Okay, now it's good. But now we still haven't passed that into the fragment shader, right? Sorry, pass into the mesh color. How we're gonna do that is actually quite simple. We use this function called texture 2D in the GLSL. So color equals to 2D. The first argument will be your sample texture. Let's give it a different name. I think texture should be some of the built-in variables that you cannot name it after. So we name it after C texture, then we have for UV, then we're gonna replace our diffuse with the text color variable. Interesting. I think I have to recompute as well. Okay, doesn't seem to sample the images correctly, image color correctly from the mesh. Yeah, I think this could be some of the bug of wrangle. Or another way around to solve this is probably passing on some of the scale to scale your texture. Sorry, be larger. Yeah, to scale your texture, just pass over the first. Then you multiply your UV by the scale. That's it. But it doesn't seem to have too many impact. Yeah, I think this is not rendered correctly because of some probably internal bugs of random. Yeah, like for example, if we render another geometry, like for example, nerves. Oops. Yep, so then you can see it's rendering correctly, right? Yep, perfectly clean. Yeah, I think I'm not sure whether, yeah, this is probably something that Red will have to fix. But this is actually how you sample, how you sample, texture and apply that to a mesh in Grasshopper. Yeah, although the texture mapping doesn't really work well, we can use another workaround here. Yeah, instead of using that as a texture mapping, yeah, we can probably use that as a shading instead. So maybe we can do some, or another possibility that causes error is probably we can slightly scale this UV, or using this one as a as a shading tool for the mesh instead of as a texture. So yeah, this is a little bit complicated. Like we have to multiply the yeah, we have to multiply the normal by the world to camera normal. World to camera normal matrix. For this step, we're gonna still use the normal arguments, but we're gonna do some displacement on your UV. Oh. Oh, sorry. Yeah, you have to get this one as a built-in variable first. Sorry. Yeah. To camera normal. We do some magic to our UV. By this is basically like using this normal to access the to apply this color instead of as a texture, but as a shading gradient. Yeah, you can find more of the mathematics behind this from the learnopengl.com, but I will not go over the details from this part. And we also gonna flip the UV value as well. Let's recompute. Probably need to scale this one a little bit. So it looks like. Yeah. Just give me a second. I'm gonna look into the. He kind of like forgot about how this normal is done because it's kind of like a long time ago. Let me try to figure it out. I think some of the APIs might have changed here. I think I need to play with the variable a little bit. Oh, I see. It should be problem with that. Yeah, this is a problem with the. I think with the chromodoris probably. Yeah, because it's kind of like kind of like the mesh that is generated is not probably not usable for rendering. So we might need to reconstruct the mesh a little bit so that it can render properly. Double check. Yeah, that's right. Yeah, I think this is kind of like their issue for chromodoris, I think. Like, yeah, it's kind of like it's basically like rebuilding the mesh UV, actually. Yeah. I think maybe we can save this by another approach as well, maybe by using unify mesh UV. Maybe, yeah. I mesh normals. Is it working? No. Oh yeah, it's working. Yeah. So I think I get the reason why this is not working here is that some of the mesh after the chromodoris reconstruction, the mesh normal is kind of like flipped. So yeah, it's like you have some of the mesh that are going into the screen and some of the mesh normals that are going out to the screen, but they are connected to each other. So yeah, if you unify the mesh normals, then it should be either inside the screen or outside the screen so that it can render correctly. Yeah. But I still don't think the texture sampling works correctly because that seems to be the bug that that has been here for a while. Yeah. Let's try to use another approach. Let's try this text cron as well. See that if that works. Yeah, I don't think the text cron is works well. Yeah, okay, but somehow you get the texture somehow as a kind of like shading ingredient for the mesh. Yeah, although the UV is not working correctly in Rhino or in chromodoris, yeah, there has to be some debugging for that section as well. But I think it's on the very low level of Rhino that caused the problem. Yeah. So now you can see with this visualization, we have 3 different sliders that we can already play with to create tons of very complicated like effects already, right? Like you can control the rotation of your chair. You can also control which index map you want to use. Also which 3D geometry you want to use. Yeah, so by tuning this 3 example, you already have a lot of like interesting effects going on here. Like the small trick for doing the interpolation together is that for example, one way you can use the same controller for the geometry and the map. so that they change at the same time. Or you can set one of them to divide it by 2, so that, for example, you don't want the mesh to change so much. So you can just like you can say, if you want to change your mesh every 2 steps, then you can use this trick to let your mesh change slower than your texture shading. You can even make it slower by dividing that by 10, so that every 10 texture you get a new mesh. Yeah, for example, these are same mesh but different texture, but then you can get a different mesh and different texture. Can also use this one to slightly tune the degree of the rotation. So yeah, by playing with all of these, you can use the wrangle slider tricks to generate some really interesting like GIFs out of your projects. So yeah, does anyone have any questions so far? Yeah, if not, we gonna.
Yeah, we can move ahead. Yeah.
Okay. Yeah, then we're gonna go on to like a smaller step forward to take a look at how the shader can be used across time. So like one thing that the shader is really good at is performing some real-time visualizations. Yeah, by real-time, we actually means that it's you can visualize your shaders. You can visualize the change in your shaders across time. So how we can do that is one of the built-in uniform for GLSL is called time. So the time is basically the time in your like system. So like for example, I want my GL position dot x. I want like there's like for example offset that equals to the sine of time. Yep, and then I want this offset to be added to the x of my mesh vertex. So we can say this by like this. Basically, maybe it's too small. Let's say we can multiply that by 10. Okay, and show that. I'll write that in that way. Maybe this is. I think. Oh, sorry. Shouldn't have directly modified this one because it's somehow oops. Sorry, this is a sad news. This is one of the bugs of this program that if you click mistakenly into somewhere, you will probably delete the entire program. Sorry, let me just redo that. This is a save my code somewhere else. Interestingly, yeah. Now that we have recovered the vertex shader, wait, the fragment shader also gets deleted. Huh. Yeah, let me recap the fragment shader as well. Recompute. Okay, now we have everything back. Yeah, sadly we have to redo everything. Yeah, but we can first visualize, yeah, how that works. Like how you can use the time to change the, some of the, for example, to change some of the, yeah, change some of the color of your. Of a vertex, say we place a shift on this one. Then say whether we can add that. Okay, this is still Web4. Maybe if we can add a shift to the entire. Okay. Yes, seems that we can, right? Like, yeah, this is basically adding the XYZ value of the to the GL position. Well, we can also add only to the X of this objects. Okay. Yeah, we can create like a offset equals to variable time plus shift. Just directly get a built-in variable from here. Time. Okay. I'm going to use offset instead here. Compute. Yeah, now as you can see here, yeah, as we as time goes, we can see the chair is slowly moving in our X direction. We can also, instead of just using time, we can also give it a sine function and multiply that by something so that your chair is swing back and forth between 2 points in the space. Yeah, apart from manipulating the offsets of your points, yeah, you can also manipulate your like apart from the GL position. Not sure whether we can manipulate the mesh vertex here. Not sure if that's possible. Yeah, it seems that the mesh vertex is not writable. It's probably like Rhino does not allow you to manipulate the vertex XYZ in real time. So Yeah, but it doesn't matter. We can add something else to the effects. For example, we can add some shapes in the text coordinates. Like say, for example, the text core here is actually the one we used as UV before. Call the UV instead. UV. Okay. This should be UV 0, 0. We can let uv.x equals to offset. Oh, sorry. Yeah, increment by offset. Compute everything. Oops. Interesting. Probably this is just too small. You can maybe need to do this instead. Yeah, maybe this has to be done in fragment shader instead. Sorry, let me check. See if that's the. If we want to here we want the type like the texture to simply float around. Yeah, across time. Let's try to do that in fragment shader. Yeah, okay. Interesting. Seems that this can be only doable in the fragment shader. Yeah. So now you have the texture now you have your 3D mesh moving back and forth in somewhere in the space. And you also have the texture that seems to it seems like a fluid or floating effects here inside the on your mesh. And you can also use, instead of using the timer or the system time for the visualization, you can also use this slider trick to control the shapes of the texture on your mesh as well. Yeah, but yeah, you can see this is real time, right? Yeah, it's pretty fast. So if you want to record some really quick demo, you can use this one. Yeah. So that's pretty much all we're gonna cover in the Grasshopper shaders. Yeah, does anyone have any questions so far? Yeah.
Did you check the question? Right? Yeah.
Good question. I am actually not sure. I don't think the texture can be the texture that cannot be exported, because this is the shader is in charge of the the rendering of the mesh, it's not actually generating a texture. Yeah. So if you really want to texturize the mesh, maybe I think you need to manually create the material somewhere in the Vray or other renders. Yeah. This is basically the same as trying to implement the renderer for using the shaders. Yeah.
But does the Grasshopper rendering helps, like Grasshopper V-Ray helps?
No, this is different system. This is the Grasshopper built-in renderer. It helps you display what is on from the Grasshopper canvas to the Rhino viewport. But it's essentially different from the Vray renderer. Yeah.
Okay, so if you have to render it real time, you will have to create the material and grind. Is that
That's
correct?
right. If you want to bake it, no, like if you want to bake it
Yeah.
into a mesh with texture, it's not doable. Yeah,
Okay.
this is more about displaying this, but I think you can already do a lot of experiments by using using the animate feature of the slider. Yeah.
Right.
This is essentially what we had in, I think, in one of the example videos. Like you can have this floating texture inside Grasshopper. Okay. Yeah. Does anyone have other questions? If not, then we're gonna jump into Unity for the remainder of today's session.
Okay. Yeah, no more questions. We do have. Yeah. Okay, we can start with the next part.
Okay, nice. Yeah, let me switch back to the PowerPoint really quick. Okay. Now we have done this very long sessions of live coding. And we also can do some animations with this setup. It's basically you use the slider animator to export the sequence of images, and you can create a GIF out of it. And you can further convert the GIF into an MOV or other like files that you want. So this is already like some very material workflow, I think. But wrangle is still not like in terms of the visual effects, it's not the expert in the domain, right? Like you have a very good geometry kernel, but the shader is what wrangle is not good at. But the GHGL is a good tool for starting learning shaders and all these visual effects. Yeah, for more advanced visual effects, we can look into another tool that oh sorry, I paused my screen mistakenly. Yeah, yeah, this is the visualization that that you can further export using the animator of Grasshopper. Yeah, but Grasshopper Rhino is not expert in such like VFX domain, right? If you want to create really advanced visual effects, you have to switch gears to Unity instead. Yeah, Unity is somehow like have a very nice personal free plan they can leverage for creating all of these visual effects. This is the Unity VFX graph, which means a lot of like CG movies or games are made with. And they also have a really user-friendly interface. So we're gonna really quickly look how how you can do you can visualize the output from the 3D GAN into the Unity setup. Yeah. So first of all, you have to select the correct rendering pipeline. So when you use Unity Hub to create Unity projects, select the high definition render pipeline instead. This one has the most stable version of VFX graph. If you're using universal rendering pipeline, there might be some issues for that one. So after you, this is like the default setting for most of the VFX. And to install VFX, you're going to use the package manager and the visual effects graph inside the Unity to actually install it. And what we're mainly focused on today for visualizing the 3D GAN output is using the particle systems. So particle system is a very common technique used in CG industry to create visual effects. So basically, you can imagine like smokes, waters, all of these can be subdivided into very sparse data structures, such as like OpenVDB. And these sparse data structures is usually voxels, and each voxel can be rendered using our shader techniques. This shader is what the VFX implements, and VFX has a very user-friendly interface that you can create really complicated shaders by using the existing systems. So each particle system have 4 parts in the shaders. Sorry, in the VFX graph. The first is the spawn. Spawn means that how soon you want your particles to appear in the scene. And initialized particle is basically tells the program what each of the initialized particle look like. And does it have like an initial velocity? An update particle tells the program how you're gonna update the properties of the particle. For example, you want to fly it to a certain direction. You want the color of the particle to change across times, follow certain patterns. And the last one is the geometry of the particle that you want to display on the screen. For example, the quad or circle, sphere, or cylinder or whatever. Yeah. So each of the all of the particle system are made with those 4 components. Yeah. And today we're going to use one of the boilerplate projects from Yuma Yaga. This person's like GitHub repo. So basically, that this project is a really nice setup for using the VFX graph together with the PLI point clouds. Sorry, let's then jump into Unity. Yeah, so as you can see here, inside Unity, if you just follow the GitHub repo that we sent into the chat, then you download the entire project, and you can open it using your Unity. So using your Unity editor. And let me repost the GitHub. Yeah, that's it. Yeah. So once you open it, you can see a lot of like stuff here going on here. So for example, we have a couple of example point cloud, like the flower and the park that the author used. So gonna first pause my visualization. Yeah. So this is the initial boilerplate point cloud that the author provided for us. So basically, that's a point cloud of a 3D scanned garden. Somewhere from the internet, and as you can see, we have this. It has a visual effects component that are attached to the point cloud, called workshop point cloud. So this one is basically the major VFX graph for this point cloud objects. And let's say, and you can see this there. It follows the same pattern that we see, that you have a spawn array, you have an initialized particle, update particle, and eventually how you want these particle to look. And you can also set the like the shape of the like each of the element. So for example, let's say, you can, I think this one. You can change the scale of each of the vertical to display. And also you can change the lifetime of the particle. Lifetime means how long you want the particle to stay alive. If you shorten it, it will be like, it means that your particle will be updated really soon. Feel free to play with some of the parameters. And here, so for example, there is also a position mapping, and the color mapping that it's already provided. For example, beside that as control. and it should be appearing. Okay. Yeah, following the order of the index in the mesh. This one is more of like a random one. Yeah, you can play with the set position from map. This is basically the core of our visualization. Is allocating the particles inside the space by following the like following the geometry of our point cloud. Yeah, I don't think there is a way to set the scale of the particle. Oh yeah, here it is. Sync. Yeah, this is the core of the particle. Sync. Yeah, this one. Yeah, this one is basically trying to. Yeah, this is basically trying to give the particle sort of like initial, like some speed. Yeah, some speed for the oops, across the lifetime. Make it smaller. You can also let it follow the original color. Yes, you can see it's already creating a lot of like really complicated visual effects. Yeah, so we can easily import our point cloud files using the asset import function, import new asset. Yeah. Be sure to remember to import our binary PLS instead of the ASCII PLS. Otherwise, Unity will raise an error. Yeah. So let's say, for example, I've put out my binary PLS here. Yeah. And once you have imported them, they don't look like this. They're gonna look like a mesh. And you have to convert the mesh to a texture to make it work. Yeah, let's say for example this one. This is the flower, right? You click into it, you're gonna see that it's not a real. It's not yet a texture map, right? It's if you open that with the mesh map, you can see that's a point cloud of a flower scale. So it's a mesh, but we have to turn that into a texture map to make it readable by the particle system. Yeah, and you have to click apply, then you will just convert that from a mesh to a position map. Okay. So let's drag this position map to the particle system. Well, now you can see there's some interesting change in the scene, right? Like the flower garden is changed to something like this, changed to the vase. You can also drag some of the this one. Drag some of the position maps of the point cloud that you imported to see what that looks like. Yeah, I just need to scale it up. Yeah. Now here we go. We have the chair. You can also, yeah, you can also like change the chair mapping by manually dragging some of the position maps to this one. Because I use a latent walk to sample all these chairs, right? The previous one doesn't look so much different. But if I choose another chair from a different latent walk, you can see it's already looking quite different. And for the color, you can even give it a completely random color. Yeah, for the size, you can what you can do here is you can actually also do you can set the scale by different side functions of this time. Give it a try. Let's say the max is 20. Yep, so it has the sense of like the size of the point cloud is changing drastically across time. Yeah, so that's how it works. You can also make the duration longer to see some of the effects. Yeah, just play with this kind of like parameters. Yeah, and yeah, that's a lot of fun actually working with this kind of stuff. Like you can also give it a force to let all the particles move along certain directions. What's even more interesting is that once you have all these files, you can also create a Unity script to loop over all your 3D GAN objects and kind of like and update them during runtime like this. This is like a real-time latent wolf in Unity, but with cooler visualization, right? It's better and much faster than Grasshopper. Yeah. So basically, it is using the same similar VFS graph. Yeah, I can also give it a track. That it has some like displacement. So if the intensity is 0, it will not be moving anywhere. But if you give it some of like drag, yeah, we'll have a interesting displacement over time. And also change the direction of the drag force so that the particle looks like it's dragged towards different directions. Make this more vivid by yeah, you can raise the lifetime of such particle. It's look fluffy. Yeah, how to write this kind of like auto parsing script for getting all the binaries. It's actually quite intuitive and easy. Let's say first you have to expose the text position map property of your VFS graph. Yeah, to do this, you create a variable here, somehow like you can call it texture2D. Let's say, yeah. and you drag that postmap new into your screen, into your VFS graph, and connect that to the start position from it. Now there is actually nothing here, right? Like, yeah, there's nothing yet here in the script. So you cannot see any point cloud because it's empty. Yeah, but we can randomly select one of the position maps, attach it to it. But now this is still a constant position map, right? We don't want to manually drag the position map onto the graph to be able to see the visualization. We want to have an automatic script to automatically loop through all the point cloud objects to be able to do this interpolation for us, right? To do that, we're gonna create a new script called latent walk maybe. I'm gonna turn off the previous one. Yep. And let's start do some coding in Unity so that this script can help us like grabbing all the point clouds in Unity and update that in real time. Yeah. If we click into double click the script, Unity will pop up this editor interface for us. So we have this model behavior script called latent walk. Yeah. So basically, what we're gonna do here is that we want to loop through all these point cloud objects in the asset and load them and update them every certain time frame. Yep. So we're gonna first inspect how this asset is composed of in our Unity editor. Yeah. You can see this one is actually called baked point cloud if you double click onto the asset. Yeah, so it's under the namespace PCX, which is point cloud importer created by Casual. Yeah, very famous VFS artist. And each of these class has an attribute called public attribute called position map. This is what we're gonna get. And this baked point cloud is actually a scriptable object that we can like get from all the assets in Unity. So to do this, yep, we're gonna use some of the function that someone already wrote called get all instance. Yeah, to get the scriptable objects of a certain type. To use this script is actually already written like get all instance, but we have to use a namespace Unity editor. Okay, now this function works. Yeah, but to get the visual effects, we're gonna also be using Unity namespace Unity engine VFX because we want to access our visual effects graph in real time using this model script. So we can set this as a private attribute. Visual effect VFX graph. And we're gonna get the VFX graph on start. Component, visual effect, start. Yep, and then we're gonna oh, sorry, to use the toList function, we have to also import the system technique. Now we can try to use this get all function, but we have to have a private attribute first to store all these baked point call objects. We create a list of baked point call called and you see there's an error here because we haven't imported the namespace PCX. Once we have PCX, so we have the baked point call. And then we can set point calls equals to instances. We can log the count of the attributes upon the start. And Unity auto compile the file. Clear it and let's see if there's something popping up upon start. Okay, now we have it. So there's a 402 point clouds in the projects. And now we're able to get all of them. So the next stuff that we want to do, we can first experiment with replacing the post map attribute of the FS graph in real time. We're gonna get a index attribute onto our editor, and we're gonna set the texture of new view, that of the point clouds index. If we go back to Unity, you should see our test will now have the test index, right? And it's set to number 0. So it means that we are accessing, now displaying the zeros point cloud. If we change that to a different value, well, ideally it should display differently, but now it doesn't. Let's say it's called postmap new. Should be able to set the texture. I'm not getting the wrong name. Postmap new. Let me run that in runtime. Yeah, the start might not be triggered during the editor time. Okay, I think it should work enough. As you change the test index here in Unity, you can see that the shape of our point cloud is changing. Because we are actually looping through the different postmaps of the point cloud that we import. And it's a real-time, very fast and efficient, like like 3D latent mode. Okay, I see. Yeah, in order to let this script execute in editor, you're gonna have to add this decorator execute always. And it should execute regardless of whether we're in runtime or in the editor. Now you can see that even in the editing mode, we can do a little mode as well. But do not all go over the boundary. We haven't add arrowhead. Okay, but then we're gonna add a small function to let the visual effects be updated in real time. But we don't want that to be executed every frame, right? Otherwise, yeah, like Unity is updated at like 60 frames per second. It will just be one blink. Yeah, we don't actually want that to happen. So yeah, let's say we give it a control speed, test speed. Yep, excuse me. And we're gonna update our float map like every test speed. Function called handle texture update. So this is actually a generator. So enumerator means something that is like something that is you can execute this one and wait for certain seconds to execute the next. Yep. So yeah, so to do this, you just need to yield return, wait for seconds. Sorry. So whatever you do, this function will always execute only after the test speed seconds have passed. Okay, sorry, I think this there's a, oh, this is a constructor, so it's not a static function. You have to return a new wait for seconds. Okay. Now, after you wait for the seconds, you're gonna do a update of the set it to actually just use our test index actually to increment. So at the beginning we can set test index to 0. Yep, and can also use a handler to track. We have already everything. Window equals to false. We can do this. Not update everything unless there is a has handled flag. So only if has handled start one time. Whole time update texture. We're gonna also increment. Sorry, let's get the wrong function. Yeah, we update the has handled flag inside our function. Okay, seems in a good shape. Let's test whether that works. Similarly, we have to start the engine to make it work. Test index still doesn't increment. Let's say, oh, sorry, this should be false. Still. Let's do it quickly. So maybe there I have got write the logic in a reverse way. Oh, see, I think we should update the has handled. You should update the logic here to not has handled. Instead. Okay, now it's automatically performing the data space, data the work for us. You can also, yeah, you can see the index is incrementing. Always reset it to 0. You can also increase the time frame so that it's interpolating slower. So this is only incrementing after your time step, the time increment has reached your test speed. Okay, that's pretty much about the Unity part. Does anyone have any questions?
Yeah, just one more. Were you sharing anything on your Rhino screen or something while you were talking about the incrementing of time? We could only see the Google Colab screen.
Wait, what? Sorry, the screen doesn't play the Unity one?
Yeah, it wasn't playing for the last bit when you were doing it. Right now, if you were, yeah. So could you just repeat the last bit a little bit? Last few minutes, yeah.
Oh, okay, interesting.
About the time frame, yeah.
Wait, so like everything in the Unity part hasn't been shared?
No, everything was shared, just the last bit when you were changing the time frame.
Oh, I see. Like,
yeah.
Like just automatically updating the particle, right?
Yeah. Okay.
Oh, I see. Okay, yeah. Basically, I was just writing a function called handle texture update. So this one automatically updates the point cloud every few certain seconds. Yeah. So to do this, we just use the quarantine in Unity so that the execution doesn't happen every frame. Like one frame is basically, you can understand, 0.2 seconds, and it's changing too fast, right? We don't want our point cloud to change that fast. Yeah, so that we can see some visual interpolation between different geometries. So we use this wait for seconds in the enumerator as the to pause for certain seconds after we update the point cloud. Yeah, and to do this, we pass in a public variable called float speed, and this float speed is part of the Unity. You can change that in the Unity inspector. Like the test speed, it should be actually called time difference. So as you can see here, and let's start from 0. This index is updated every time speed seconds, like every 0.39 seconds. You can see the geometry is different. But if I increase the value, you can see the index is incrementing slower, right? Every 1.24 seconds. Yeah. So that's how we change the execution of the interval, or the speed of the latent walk, essentially. You can make it really fast by making it really small, like this. Yeah. So you can see there are some changes in the geometry. And it's still a real-time smooth interpolation of the 3D latent walk. If you want it faster, you just decrease the level. Now you can see the point cloud is changing faster than before, right? You can see there's a faster interpolation between different shapes. Yeah. So that's basically it. Yeah, feel free to. I think Unity is a quite fun program to play. This is you can also add some game interaction logics to this one. Like if your person approaches the chair, it will change faster or slower or whatever.
And what's the outcome of this? Do you get like a 3D output, or is it going to be a animation rendered from Unity?
This
How
one
can you export
essentially,
the outcome?
yeah, you cannot get the 3D outcome. It's still like a visual effect, right?
Right.
The only geometrical outcome we have is a PLY file. But what you can get from Unity is actually you can build it into a game. So you can select file build, and you can export this one entirely as a game. Yeah.
Okay.
Yeah, you can. I'm not sure whether this one built successfully because I haven't really tested this building process before, but we can try. But yeah, that's essentially how you create games. Unity is mainly made for game engines, or you can also do for VR experiences. For example, you can like upload your 3D guide into extra environments or things like that.
Okay. Thank you.
Yeah. So this is a kind of like a long session today. Yeah. And, yeah. Hope everyone can like have some takeaway from today's session.
Yeah. If this brings us to the end of the session, that I think it was a really interesting session. The last part one as well as this part two. I'll just remind the audience that part one is also available with the same name, Generative Game, on our YouTube channel. It's quite interesting to see the workflow and how we are using the latent space inside of both these important and technically advanced softwares. Yeah, I think Gustavo is talking about part three as well. So are we planning out part three?
Yeah, if I have some new progress, we can definitely do that as well.
Yeah.
Yeah.
Or we
There's
look forward to your workshop then.
Yeah, there's definitely like a lot of future works can be done. For example, we can add textures to the 3D game training process. Yeah, I think that would be like also a plus. Especially, you can imagine that as adding the RGBA to the mesh attribute. So it's changing from like just the 0, 1 on each voxel to 0, 1 and the RGB value. Yeah, that one can definitely bring a lot of new possibilities as well.
Right. Maybe I'll just quickly share and summarize for the event today and our upcoming events. And in case anyone still has any question and you want to ask the question directly to Jen, please feel free to raise hand or switch on your video and ask him the questions. Can you also drop in the chat an email or a place like GitHub or somewhere where the students can reach out to you?
Yeah, sure. Sorry, you mean like what is it? Sorry, can you repeat the
So
question?
yeah, can you share any place, social media link or your GitHub link where students can reach out to you?
Oh yeah, sure. Let me post that into the.
Oh, I was about to say, Jen, do you have a site that's not directly pointing to your collaborators' work? Like, do you have your own email address, like Jen at blah 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 at gmail.com? Do you have something like that set up?
Sure.
Got it.
Of course. Yeah. That's a really good point. I can leave my Gmail here. Yeah.
We can post that information after the fact, Bavleen, on the YouTube. So anyway, just wanted to give you a heads up.
Yeah. I think you can. This one is the email address that you can reach me regarding any of the 3D CAD stuff. Also I think I also have some like tutorials under the channel architecture Yeah, I can also, I think I've shared that one with the Half-Life before. Yeah, I can do, oh, sorry, it's also called Generative Game. I can reshare the channel.
Okay, so while we are exchanging our details, I'll just quickly remind our audience then in about 2 hours from now, we are going to start with our first Portuguese session, which is going to talk about new hybridities in the Portuguese diaspora. We will be live streaming this session on our YouTube. Please join in, please tune in to the channel. Tomorrow, we also have another series of lectures with the FIU DDES program, where Suzanne Schneider will be talking about AI, neuroscience, and architecture through our work. Professor Neil will be heading the program, hosting the event. And on 25th of March, we have another session or our Farsi talk on novel multidisciplinary approaches to architecture. This talk will be held in Farsi. And on 26th, at the same time, on Saturday, we have our next Digital Futures talk of this month, where we'll be talking about clay printing in architecture with some of the leading architects and designers working in the industry. All our resource material is available on our YouTube channel. Please visit. All the previous tutorial sessions are also available. And we are looking forward in expanding our team, and we welcome more applications to join our team for this summer. Please write to us if you're interested on info@digitalfutures.world. You can also join our community and connect with us over Discord. This link will lead you to the Discord invite channel, where our community is active. We look forward to your interest. Thank you so much. Do we have everything for the contacts posted as well? Okay, we have one question. Maybe we can quickly take that up.
It's three questions in one from the same person,
okay.
Pavling.
Okay, yeah. So I'll just read out the questions. I think I missed out on the first one. We have questions regarding how to generate array of chairs.obj file before running the binworks, and if I need to create a new test, change chair to some other object instead, how do you do that? And the second part of the question is also, do I need to find OBJ resources one by one, or is there a simple, efficient way to do so?
I think in the first session, we covered the topics of like some 3D data sets. Yeah, there's one called, I think, 3D ShapeNet that has thousands, or at least not thousands, maybe just like not just thousands, but tens of thousands of models for each category of 3D objects. Yeah, there are tons of OBJs on there. You can use them to grab some data that for the training. And also wrangle, you can use wrangle easily to convert like file formats from like PLA OBJ to each other. Yeah, wrangle have a command line option to do that. So you should be able to like transform between different file formats without any problem. Yeah. But there are definitely like when it comes to architecture, 3D dataset is quite limited. Yeah, so yeah, that's why I've also created the generative game like initiative to gather the architecture dataset, because it's there is no such datasets there. Yeah. sorry, did I answer all the questions?
Yeah, sorry. I think there was one more question, which is more related to 3D GAN, VQ GAN plus clip plus texture. Is that possible to do that, to use that as a workflow?
Yeah, I think that's definitely possible. Like if you can, like you can use VQ GAN clip to generate like sequences of images or videos, right? So once you have the image sequence of videos, you can use the same way that we do the texture mapping in Grasshopper. You can map that onto your mesh, right? Or you can use that as a texture mapping in Unity as well. Yeah, yeah, this is definitely doable. I think that's a really nice idea. But this like 3D GAN itself cannot be connected to the VQ GAN. I think there's different network structure. If you want a 3D version of VQ GAN and clip, there might be some other work to do, I think. Yeah. But that's a really nice idea, I think, yeah, to connect the 3D geometry to language.
Jen, I just wanted to actually ask you, what would you say to someone that is new to this, Mac or PC or Linux, that wants to dive into your research in gaming and kind of coding this up, thinking through it as an architect? Like what advice would you give?
Yeah, that's a really good question. It's really a long story. Like I think, but basically, I think maybe the one thing that you can start with is with some like free mode courses to learn programming. That's at least how I did when I was still in the architecture school, to just self-taught some like basic fundamental knowledge of programming. Yeah, and I think there's tons of like book resources out there that are free and very helpful. Like for example, like the CS50 at Harvard. Also, the MIT has some Python related courses like 6001X or 602X. Stanford also have the famous machine learning course by Andrew CS 229. Sorry, yeah, 229, and also CS 231. Those are all very helpful resources to start with, I think. For Unity, I think YouTube also has a lot of Unity tutorials. Yeah, that and also Unity itself have something called Unity Learn. Yeah, they have a lot of courses on there as well. Yeah.
Thank you very much, Jen. I really appreciate it. I had a really good time, and I've heard from other social media sources that they're going to use it for their classrooms to try to get these people started on AI. So thank you very much for your time and your talent. And I look forward to part 3.
Yeah.
Thanks so much for organizing this amazing event. Yeah.
Yes. Thank you so much. It was a long day for you. Thank you. Okay, bye-bye. Yeah.
Oh, do we have the final slides to go over the, did you go over the slides for the reminders?
Yes.
Got it. Thank you very much. Bye, Jen. Really appreciate it.
Yeah, great. Thank you, everyone.